Okay, the decay process. So if we recall back of the number of neutron versus atomic number Z, the stability, the line of the stability for the nuclei, right? We have dash line here where N is equivalent to Z. Okay, as we know, starting from 20, the atomic number of Z of 20 for the element, the stable nuclei deviated slightly because of the increment of the atomic number, okay, where increment in protons within the nucleus, causing the Coulomb force going to be more effective, bigger and bigger. Therefore, to counterback that, okay, we need to add up, okay, neutron into the nucleus. That is why it's deviated slightly, lift up like this. However, okay, until the N is, until the Z is equivalent to 83, adding up more neutrons not going to help anymore to stabilize the nuclei. Okay, so from that, the nuclei that we observe is going to be unstable nuclei, right? So that is where the decay process going to take place. So if we refer to this diagram, this is a bigger picture. Okay, for the N versus Z, starting from 65, okay, somewhere here, to 80. So within this column, okay. So with this band, right? So we make it bigger like this, right? So if we see here, the blue color nuclei here tends to decay or release beta or electron. The black color nuclei here are the stable nuclei, right? For the peach in color here, or slightly orange here, okay, tends to do beta or release the beta positron, or another option is actually by electron capture. What is electron capture? Madam will discuss detail after this. And for the light color of nuclei here, okay, it tends to release alpha particle. Why is this happening? Because for the blue color nuclei here, okay, they are actually neutron rich. Okay, that is why they tend to release beta, right? For the orange color nuclei here, they are proton rich nuclei. Okay, that is why it tends to release positron, okay, or also symbolized as this, right? Or by process of electron capture. Okay, this is releasing, this is capturing of electron. Okay, and for this area, the nuclei also has proton rich condition. Okay, so it tends to release alpha, okay, or helium-42, right? So let's take a look on each of the radiation decayed by the unstable nuclei. First one is alpha decay. So as I mentioned just now, alpha is actually helium-42. Okay, so if we refer to this example, okay, before the decay, originally we have radium-226. Okay, this is a A, this is a Z. Okay, At this instant, kinetic energy of the radium is 0. Momentum of the radium also 0. Okay. After the decay, what will happen? The radium going to decay 1 alpha, right? It becomes radon 2 to 2. Okay, because it release alpha consists of 4 2. Remember, alpha is actually helium 4 2. That is why the radium, okay, releasing or reducing 4 of its A and 2 of its Z. Right? So they're going to split. Okay? Here will be kinetic energy of the alpha, and to this direction the radon going to move with its own kinetic energy. Momentum as well. So all the time, conservation of kinetic energy and conservation of momentum must be fulfilled or obeyed. So in terms of decay equation, schematically, this is the decay equation for alpha decay. Right? So originally, this is the parent nucleus, we call it. Okay? As the X here is the parent. Decayed become daughter. The Y here known as daughter nucleus plus 1 alpha. So if in terms of A and Z, okay, it must be conserved, remember. So for the daughter nucleus, it has less 4 in terms of A compared to the parent, and less 2 of Z in terms of the compared to the parent's nucleus. For example, uranium 238, okay, decayed 1 alpha to become thorium, right? Thorium. So it reduced in terms of A by 4 because it's given up to this. Reduce the Z2 amount to given up to this. Another example is radium 226 become radon 2 to 2. Okay, so again, the A and the Z of the daughter is less in amount, 4 and 2 to give up to helium. Right? Now let's move to beta decay. For beta decay, again we are going to use the same method. This is the parent nucleus. This is the daughter nucleus. Because the electron, also some books put it like this, 0, -1. Right? Now, so it is understood that for one electron, it has the A is 0, the Z is -1. So again, must be conserved. Why is it incomplete expression? Okay, because there is one thing left. On the coming slide, Madam will explain in detail about this. Right, so for positron, the release of the positron in here is supposed to be 0 and +1. Right. For example, carbon 14. Carbon 14, okay, decayed 1 beta or negatron or electron to become nitrogen 14. Right? And for nitrogen 12, okay, to decay become carbon 12, it decayed 1 positron. Okay, this is an example. So here are the graph of the number of alpha particles versus kinetic energy, number of beta particle versus its kinetic energy. For the alpha particle, it is observed that the energies are discrete. Means that certain amount only. Okay, a few values only. But in contrary to that, the observed energy for beta particle are continuous, having all values up to maximum here. Right? So whenever we have this kind of pattern, and by further investigation from the scientists, it is figured out that, okay, for this expression, there are two things are not conserved. Okay, the kinetic energy and also the angular momentum of the beta particle are not conserved. Then scientists figure out about another element known as neutrino. Okay, to complete the decay process for beta particle. Right. It begins with 1930. Pauli proposed third particle must be present in decay products to carry away missing energy and momentum. And Fermi, direct Fermi, later named particle neutrino. What does that mean by neutrino? Little neutral one. Had to be electrically neutral and have little or no mass. Okay, so finally they figure out that neutrino now symbolized as mu like this. Okay, grid nu. Finally detected experimentally by 1956 by Frederick Reines. This is the history of how the neutrino is figured out. So what is neutrino? The properties of it has zero electric charge. First thing. The mass is very, very small. Okay, it consists of spin of it is half. Why is it half? To conserve, to complete the beta decay, the angular momentum within the beta decay. It interacts weakly with matter. So this is basic idea of what neutrino is. So now, the beta decay process now can be rewrite into a complete expression by this. When you have beta decay, or electron or negatron is released from parent nucleus, okay, it must be followed by anti-neutrino. The bar here, okay, representing anti-neutrino. If the parent nucleus decayed positron, okay, or positive of beta, and also a daughter nucleus, it must be followed by neutrino. Okay, so nu here having no bar known as neutrino. This one is neutrino. And this one is anti-neutrino. Right? What's the difference? It's just like positive and negative, right? So want to complete another one, just in opposite. Because this one is positive, so it must be followed by neutrino. Because this one is negative in charge, so it must be followed anti-neutrino. Alright, they are in opposite spin actually. To talk in detail about this is involving the spin, the arrangement of the spin. For example, carbon 14 decayed become the daughter of it is nitrogen 14 plus negatron followed by antineutrino. Then from here, the spin, the angular momentum, the conservation of energy, conservation of angular momentum are fulfilled. So goes the same to the nitrogen 12. To decay become carbon 12 plus positron followed by neutrino. So in terms of schematic diagram of visualization, this is the way it happened. So talking about electron capture just now, this is a special case. Instead of the parents decay, okay, become daughter plus an electron or negatron, the parent also can capture its own, okay, its own electron, right, from its own orbit. Okay, so you will see, if you figure out this in detail, you will see there is K capture, there is L capture, but most of the time it's K captured. What does that mean? The electron being captured coming from K shell. What is K shell? Is the energy level, the lowest energy level within atom, right? So for example, beryllium, okay, going to capture one of its own electron to become stable, to become lithium plus neutrino. Carbon dating. So the beta decay of carbon 14 to be carbon 12, okay, is commonly used to date organic samples, living things, right? Cosmic ray in the upper part of our atmosphere cause nuclear reaction that creates carbon 14. The ratio of carbon 14 to carbon 12, right, in the carbon dioxide molecules of our atmosphere has a constant value of approximately to this, right? The carbon atoms in all living organisms have this same ratio of carbon 14 to carbon 12 because the organism continuously exchange carbon dioxide with their surrounding by breathing, right? When an organism dies, however, it no longer absorbs carbon 14 from the atmosphere, and so the carbon 14 to carbon 12 ratio decreases as the carbon 14 decays with a half-life of 5730 years. It is therefore possible for us to measure the age of the organic material by measuring its carbon 14 activity, such as done for the Dead Sea Scroll. So example 43.9, radioactive dating. So this is one of the application by using the ratio of carbon 14 to carbon 12 just now to date, okay, how long the organism being dead, right? A piece of charcoal containing 25 grams of carbon is found in some ruin of an ancient city. The sample shows a carbon 14 activity R of 250 decays per minute. How long has the tree from which the charcoal came been dead? So as we know, ratio of carbon 14 to carbon 12 must equivalent to R0 as stated before. And we know that activity for carbon 14 R is equivalent to R0 E negative lambda T. So our interest is now is the T. So rearrange the equation, you will have this pattern. 1 over decay constant or lambda is equivalent to this. R0 is equivalent to lambda N naught of what? Of carbon 14, remember. Okay, so N naught of carbon 14. So lambda itself again, ln 2 over T half. And N naught, okay, coming from this, okay, must be, for carbon 14, must be R naught times number of the nuclei for carbon 12, right? So R naught times number of nuclei within carbon 12 can be figured out by this, right? Which is R naught times mass of the carbon 12 to the molar mass of it times Avogadro number. This is the purpose to figure out number of carbon 14, okay, at T equivalent to 0, right, step by step. This one, we substitute the ratio, the constant value here, to figure out the number of carbon 14. So let me highlight, okay, this is a process of it. Right. So then, okay, this is the same thing. Okay, after that you substitute every single information, you will get the ratio is 0.667. So what is the T? This is the R over R naught. This is R over R naught, okay? The R over R naught is equivalent to this. Okay, then you're going to substitute into this equation and figure out the T is 3.4 times 10 to the power of 3 years. So this is the time of how long has the tree from which this kakao can be dead. So confirm it's from ancient city. Alright, gamma decay. Some element or nuclei, after it release beta or alpha, it is still in excited state. The star here representing there is excess or extra energy within this nuclei. So the extra energy going to be released in terms of gamma. Right. So as we know, gamma has no mass, has no charge. So there is no difference in terms of A and Z of this nucleus. Right. For example, boron, okay, decayed by one beta or negatron, become carbon 12. This carbon 12 is within excited state, or there is excess or extra energy within carbon 12. Okay, of course we know, followed by the negatron or electron decay or beta decay, there is anti-neutrino here. Right? And this carbon 12, the excited carbon 12, going to release one gamma. In terms of A and Z for the carbon 12 has no change because gamma has no mass, has no charge. So this is energy level of the boron 12, our example just now. Okay, released one beta, become carbon 12. Okay, carbon 12 within excited state. Okay, going to release one gamma. Okay, you see the arrow here representing this is a photon, a wave. Okay, or energy released. So become carbon 12 in stable state. Right. Another option, it could be from boron, okay, directly become carbon 12, releasing an electron or beta. In this decay process, the daughter nucleus carbon 12 is left in the ground state, okay, or stable state. So there is two ways of boron to become carbon 12, whether by decaying directly one negatron or beta, or one negatron or beta, but with the daughter nucleus of carbon 12 in excited state, and then finally release one gamma to release the extra energy. So in conclusion, we can see that listed here various decay pathway. For alpha decay, this is the decay equation of it. For beta decay, for positron or positive of beta decay, we call it positron. For electron captured, okay, and now for gamma decay. Okay, for radioactivity, actually we have two kind of radioactivity. It could be natural radioactivity. By nature, it is created by Allah Ta'ala. Okay, and also can be artificial radioactivity. So by nature, natural radioactivity, we have uranium series, actinium series, and thorium series. So this is going to happen by natural, right? So starting isotope for uranium is uranium-238, actinium for uranium-235, okay, thorium, start with thorium-232, okay, so end product or stable product of it is plumbum. We have plumbum-206, plumbum-207, or plumbum-208, right? So the one that artificially done in lab is actually Neutronium. So Neutronium here, okay, it start with Neutronium 237 and up with bismuth. The half-life here is long, okay, power of 6, right? So this is the decay series. For example, starting with thorium 232 and finally become plumbum 208, right? So the decay series take lots of years, right? So within the journey, the thorium become radium, radium become actinium and thorium, and then again and again within the process it's going to release alpha, beta, gamma, okay, so many. So this is one of the diagram for nuclear reactor, okay. So big because you have to accelerate the electron, proton, neutron and bombard them, and then the nuclear reaction going to take place and so on. Nuclear reaction, if let's say you have particle A bombard into nuclei X, okay, where the output of it become nuclei Y plus particle B. Okay, if this is a nuclear reaction of it, we can also write it in terms of expression of this. It means that A is bombarded into X, producing Y with B. For example, okay, lithium is bombarded with proton, alright, producing 2 heliums. Alright, so in terms of decay equation in simple manner, we can put it like this. It means that, okay, lithium is bombarded with the proton, producing helium, okay, plus alpha particle. Right. So in general, okay, nuclear reaction take place when you have nuclei X, okay, a radioactive material, is bombarded with 1 neutron, okay, producing, okay, the X with excited energy, excited state, then finally releasing, okay, 1 gamma, for example. So hydrogen, for example, bombarded into F19, producing oxygen plus alpha particle. Okay, so in nuclear reaction, we have two kinds of nuclear fission, okay, where the atom, the mother or the parent nucleus is split into 2 daughters. Okay, so separation, fission can be considered as separation. So neutron bombarded to uranium-235, producing uranium in excited state, and finally become X and Y plus another neutrons. Okay, for example, neutron bombarded into uranium-235, okay, producing barium plus kryptonium plus another 3 of the neutrons. So this neutron going to bombard another 3 uranium, because this is only for 1 atom of uranium. Okay, we are not going to use only 1, right? Okay, for bomb or nuclear reactor, normally we are going to use 1 gram, 1 milligram. So within 1 milligram, okay, how many number of uranium exists? So in this case, we are going to have chain reaction where explosion going to happen, or we call it as nuclear fission, right? And then this is another example that most of the time happen. Okay, this is fusion. Okay, in opposite to fission, we have another type of nuclear reaction, which is fusion, where we combine 2 element or nuclei to become another nuclei, and then it's going to release whether electron, positron, beta or alpha, or also gamma, right? So most of the time this is happening at the sun or stars. Okay, terrestrial fusion reactions at the star, okay, releasing amount of energy. This is the energy that Allah created that transferred to us, okay, from the sun. That's all for this topic. Thank you very much for watching. Do not hesitate to ask any question regarding this lecture to me. Assalamualaikum.